what we got going on is more molecular shapes. Okay, so we talked about linear, and we talked about the trigonal plane and the trigonal pyramid. Now we're going to do some examples of some of the other shapes. And why don't we go with the two types of vents? We'll go with the simple one first. Alright, so we got H2O. And what do you guys think? What's the number for oxygen? Periodic table. 1, 2, 3, 4, 5, 6. There we go. 6. 1, 2, 3. Oh no, I'm doing it. Sorry, we're doing this in prep chem, so we do it the basic way. 1, 2, 3, 4, 5, 6. This is a simple one, so you can do it the basic way. This is what they did when I was in middle school. Apparently, nowadays they don't even teach this in middle school. Hydrogen just has one dot, and then we can connect the single dots. So that's like this basic way. But as we found out when we do some of these trickier ones, like an expanded octet, basically it will not work. So you got to do it the IB way, and that is having at least one bond connected to each outer atom. And oxygen has 6, hydrogen has 1, and there's 2 of them. 6 plus 2 is 8. 1, 2, 3, 4, 5, 6, 7, 8. Why don't I fill them on the outer atoms? Because hydrogen and helium are those exceptions where they just need 2, not 8. Alright. And then the shape, if I have 2 outer atoms, it's either bent or linear. And we said that linear has 0 lone pairs on the center. So if it has lone pairs, then it's got to be bent. So we're going to call this bent. And the rule of thumb is 2 outer atoms, also called terminal, but that can be a confusing word, so I just say outer. 2 terminal atoms, and in this case, 2 lone pairs on center. Bent is called bent. Alright, it doesn't look bent, it looks kind of linear, so you're going to want to show it like this one when you do it. So it turns out like this. To show that it isn't bent. Alright, let's do another form of bent. So, just quickly finding one. O3. So doing it the IB way, I'm just going to have 1 O's in the center, and then you got 1 on the left, 1 on the right. And oxygen has how many valence electrons? 6. 6 times 3 oxygens is 18. Fun fact, O3 is ozone. So it protects us from all the harmful rays from the sun. So we got 2, 4, 5, 6, 7, 8, 9, 10. 2, 4, 6, 8. All maxed out. 11, 12, 13, 14, 15, 16. 2, 4, 6, 8. It's maxed out. I used up 16, but I have 18. So the extra ones I put on the center. So there it is. But I got a problem because oxygen in the center has 2, 4, 6. It wants to have 8. So I'm going to have to do some sharing. So I'm going to take 2 from the oxygen and just kind of push them over to share. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. I didn't add or take away anything. I just did some sharing. However, this is a resonance structure. A resonance structure means that why do I share from the right one? Why can't I share from the left one? Well, I'm going to share from both simultaneously. How do I draw that? There's 2 ways. One way is put it in brackets, and draw the other possibility. So it's the same thing, it's just kind of like backwards. The double bond is on the left side instead of on the right side. And I put it in brackets. That's called resonance structure. Really what's happening is I don't have a double bond and a single bond. That's not true. I have a total of 1, 2, 3 bonds across 2 bonding planes. So really I have 3 halves of a bond, which is actually 1.5 bond. So this is kind of still misleading, showing these 2 different structures. It looks like I have a double bond like that. Both my bonds are 1.5. So another way of drawing it would be, and just a side note, Lewis dot structure examples, this is actually a resonance, which we have space for on the back, but just don't mind that. So I'm going to put this just like this, and instead of drawing a single and a double bond, I'm drawing a bond and a half. And I'm going to show that half or partial bond by a dotted line. And I'm going to have just 2. They say like, well, I'm missing some, like, where are those going? Oh, I gotta show them. Yeah, and it depends on which source you see, so you might see it where you have an extra dot. The most common source is you're going to see it like this, because then you just count. When you're counting them, it's 2, 4, 6, 8. Basically, how do you draw this in a 2D loose structure that makes sense? It's difficult because you're drawing something that you can't see. You're trying to show something that you can't see. So there's multiple ways to represent it. The main idea is the bond in those atoms, not a single. Alright, so, but in general, if you have 2 outer atoms, it's either linear or bent. The lone pairs makes it bent. Oh, we forgot to talk about bond angles and all of them, so we'll get to those. Alright, so, but anyways, we got 2 outer atoms. And only 1 lone pair. So what is that going to change? Well, the thing that's going to change is the bond angle. So if you got a bent molecule with just 1 lone pair in the center, it's a bond angle of 120. Yeah, 120. 120 degrees. And but if you have 2 lone pairs, it's going to be less than 1.5. Less than 9.5. So having just 1 lone pair is going to make it obtuse. 2 lone pairs makes it more acute. Obtuse, acute. Okay. Taking a step back, I forgot about all the bond angles for trigonal pyramidal. Trigonal pyramidal is going to be the same as bent with 2 lone pairs, because you got 1, 2, 3, 4, 1, 2, 3, 4 electron groups if you count the bonded pairs and the lone pairs. So it's less than 109.5. Trigonal planar is going to be 120 degrees. And linear, of course, is going to be Quetelet's geometry. The line is 180. Good. That's... Everyone should graduate knowing that, otherwise you won't know what they're talking about when someone's skateboarding. Except when you skateboard, you don't do a 180. Or no, yeah, you do. You turn around. Alright. We're going to come back and talk about hybridization on all of them, so we'll skip hybridization for now. Just focusing on Lewis dot structures and bonds, angles, and shapes. Alright, those are the 2 bent ones. Let's see, another one. Did we do tetrahedral yet? No, we didn't. So let's go back to a simple one. CH4. Carbon is the ultimate central element. It's got 4 bonding sites, so it's always going to be centered. And we got to have at least one bond to each of the hydrogens. Alright, and I'm being sloppy with drawing these shapes. Technically, that's not what it's going to look like in 3 dimensions. First, let's count how many valence electrons we need, and then we'll talk about drawing the correct shape. Carbon is 4, hydrogen is 1, and there's 4 of them. That equals 8 total. We got 2, 4, 6, 8, and it's all set. That is CH4. And this is a tetrahedral shape. Tetrahedral. And it's the only shape that has 4 outer atoms. 4 outer atoms, 0 lone pairs. And notice this shape right here. This is how it's shown in 3 dimensions. There's a couple of ways you can draw it. Here's one way. It's just showing that it's not perfectly like an X. It's 3 dimensions. And to get even fancier, you can show the filled in line or the dashed in line. Alright, and the filled in line represents going into the dimension, and the dashed line represents coming out of the dimension. So it's just to show 3 dimensions. Speaking of 3 dimensions, NH3 up here is doesn't really look like we drew it 3 dimensions. So that's going to be written just like the tetrahedral version. Do they have it on here? Yeah, right there. Pyramidal with a lone pair in the center. Where is that? And if you mix up the dashed and the solid, I don't think it's going to be a big deal. Again, it's kind of sloppy. But that's neat. I should have pushed these a little bit closer so it actually looks kind of like a pyramid. And then this one is, not the best drawing. I want to show a 120. It looks like a 90. So when you're doing these, you do want to try to show the shape. So you might have to draw it a second time after you identify what the shape is. But basically, the shape would be more like that. There you get a nice 120 bond angle, and then not have the dots. Right. Alright, and then the bent one, you'd also want to show the shape would be like that. Just showing the 3 dimensions. IB is really particular on that. They want to see the 3 dimensions in the drawing. Alright, that was tetrahedral. We got to get the bond angle. Bond angle is going to be exactly 109.5. Going on to the 8th type of shape. Alright. We did pyramidal. Yeah, so that's the basic ones. So now we're going to do the expanded octet. We did one expanded octet already when looking at linears. There's 2 types of linears. So why don't we do trigonal bipyramidal? So PCl5 is the example. Central atom's going to be the one at least 5 typically, or the one with the most bonding sites. P has 3 bonding sites. I know that because P has 1, 2, 3, 4, 5 outer electrons. So remember, this is going to look like nitrogen, where we have 1, 2, 3 bonding sites. So that's why it's the center, where chlorine is going to have just 1 bonding site. So let's do Cl. Oh, there's 5 of them. So going into the page and out. So, okay, so we got 2, 4, 6, 8, 10. First, we got to count the valence electrons. Phosphorus has 5, chlorine has 7, and there's 5 of them. 35 plus 5 is 40 total. So I got 2, 4, 6, 8, 10. I'm going to add 6 more to each of the outer ones. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, makes it to 40. Perfect. Alright. So this one is trigonal pyramidal. Trigonal pyramidal. Alright, and the bond angle for trigonal pyramidal, this is actually in your packet, this sheet. We got trigonal, oh, did I write bipyramidal? Bipyramidal, trigonal bipyramidal. 90 and 120. So the 120 is this middle part, and the 90, of course, is the up and down. So 90 and 120 are two bond angles present. And the rule of thumb is if you got 1, 2, 3, 4, 5 outer atoms, probably, well, you could be square planar. It's a possibility. So we got to look at 5 outer atoms plus 0 lone pairs on center. So those are the conditions for trigonal bipyramidal. So you might have to draw it and then be like, oh, that's trigonal bipyramidal. So now I'm going to redraw it so it looks more beautiful. All right. Next one. Why don't we try a seesaw shape? What do I have again for seesaw? SF4. Alright, I got SF4. I know fluorine halogens are probably terminal or outer atom. So my center is going to be sulfur. Let's count how many valence. Sulfur has 6, fluorine has 7, and there's 4 of them. Sometimes 4 is 28 plus 6 is 34. So there's 34 electrons. I'm going to put sulfur in the center. We got F, F, F. I'm going to just kind of, I'm modeling it, I'm drawing it, probably not the correct shape, but this is just a starting point. We got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, I got 2 more. Any left over I put in the center, so it looks like I'm breaking the octet rule here, having 10 electrons around the sulfur. So, rule of thumb, if you got 4 outer atoms, and 1 lone pair on center, this is going to be seesaw shape. Seesaw. And a seesaw because that's what it looks like in a 3-dimensional plane. This doesn't look like a seesaw right now the way I drew it, so I'm going to rewrite it. Which other one has 4 atoms? 4 outer atoms? Tetrahedron is 4 outer. So it has 4 outer atoms and 1 lone pair on center. Well, now it's going to be seesaw. And where's the picture? There's a picture of seesaw. This is like a sideways seesaw. Not like that. Like if you look at it right there, now that looks like a seesaw or a teeter totter. Yep, on the test it's going to say draw the 3 dimensions of it. So we got fluorine, and then you put all the dots. But it might be hard to know, oh, right away that seesaw just by looking at it. So you might have to do a rough draft and then a final draft in the correct shape. And the bond angle for Seesaw is less than 90 and less than 120. So right here, up and down, apparently it's going to be a little bit less than that. And right here on the, what do you call it, the bottom of the seesaw, I guess, would be 120. So less than 90, less than 120. Alright, we got till 25. Yeah, okay, that's where I was confused yesterday. There was some logic to my misconception. Alright, moving on, I'm just gonna use this area. So, exceptions to the octet rule. So we already talked about that. We already kind of talked about that. We're gonna do some more examples that will cover those. Number 10. Let's see, what's another example? Let's do T structure. So an example of T structure, ClF3. Oh my gosh, that's tricky. Cl has one bonding site and same with F. So in this case, the one in least supply is probably going to be centered. So Cl. So we got Cl, F. I'm going to do a rough draft and then a final draft. And got some news for you. On the test, most of the questions are going to be so those are the harder ones. Let's see, Cl, F3. Oh, Cl has 7 and F has 7. 7 plus 7 times 3 is like 28. So we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I got 4 more to put. 26. Alright, so I'm going to then redraw this, but I gotta think, alright, 1, 2, 3 outer atoms. So this definitely has 3 outer atoms. Really the options are trigonal, planar, or trigonal, based off what we know. Planar has 0 lone pairs, pyramidal has 1 lone pair. But now this one has 2 lone pairs, and we said that this was the T structure. 2 lone pairs on center. I mean, it has more than 2 lone pairs overall, but center is the best. Alright, bond angle of T structure is less than 90. Hey, it looks like a T. Put it like this. Imagine that. I guess that's where the name comes from. So less than 90. Alright, T structure. So let's make this look... Hey! It actually looks like a T, so I don't have to change it. Here's my T. Alright, number 11. How many shapes are there? 6. 13. Getting close to the end. What do you do? No, it has 3 outer atoms, but it doesn't have 5 electron groups. So, like this right here is talking about electron groups. So that's the non-bonding and bonding pairs of electrons. We got 1, 2, 3, 4, 5. Here we got 1, 2, 3, 4, 5.
Also, 3 of them are the atoms. Or no, 2 of them are the atoms.
Two of them are lone pairs, and 3 are bonding pairs. If you're talking about lone pairs, there's 2. But yeah, good point. All of them have, in this section, 5 electron groups, which is lone pairs and bonding pairs with the terminal atom. Alright. Oh, we did linear already. So boom, that's an expanded octet. Why don't we do octahedral? That's probably the simplest of all the expanded octets. Octahedral, where's my example? octahedral. We'll do PF6 minus. So we got to have P connected to F. 1, 2, 3, 4, 5, 6. I got to count the valence electrons. 5 for phosphorus, 7 for fluorine, and there's 6 of them. Plus 1 because it's a negative charge. 6 times 7, that's 42. 47, 48. Oh, I already drew it. We got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. Perfect. We got our 48 that we needed. So that's octahedral. I know it's octahedral because it's the only one that has 6 outer atoms. 6 outer atoms, 0 lone pairs on center. It is octahedral. Shouldn't it be called like hexahedral? It's got 6. Well, octahedral is referring to the number of different bond angles that are present. The 2 types of bond angles that are present are 90, 90, 90, 90, 90. 8 different spots. There's a 90-degree angle. Alright, let's do, we got 2 more, square pyramidal. Looks like, yeah, let's go for it. Square pyramidal. BRF5. And again, BR is going to be the center atom. And I'll leave you at a cliffhanger for tomorrow. So, wait, we do end it. Okay. Alright, so that is the conclusion of today. We are going to finish this up tomorrow. Hope you enjoyed yourself.